Okay, this chapter deals with Newton's 3 laws of motion. We have a lot of goals to cover with this chapter. The important part is going to be Newton's 3 laws of motion, and these 3 laws of motion are going to relate this quantity force to the position, velocity, and acceleration that we've learned about already in 1, 2, and even 3 dimensions. So we're going to describe force as a vector and talk about how to combine forces. This is simply vector addition. Very importantly, we're going to talk about the relationship between mass and weight. They're not the same thing. Also fairly important is we're going to learn how to draw free body diagrams of forces. So we've already talked about the motion in the dimensions, but we haven't talked about what causes that. We know that if something's accelerating, the velocity is increasing linearly with time and the position is increasing quadratically with time, but why would the acceleration be changing? Now, a fellow by the name of Sir Isaac Newton came up with these 3 laws, and the interesting thing about them is Newton was able to deduce this law entirely using the scientific method. He made observations of some physical quantities and conducted lots and lots and lots of tests. So he had a theory, and it was tested sufficiently such that we can say that it is a law. Now, these laws are very simple to state, but applying them can be intricate sometimes. So let me talk about this thing called a force fairly quickly. A force is going to be an interaction between 2 objects. In the case of this guy right here, it's an interaction between the hand and the block. Or it could be between an object and its environment. For example, if an object is falling and is encountering some air resistance, that is a force of friction. And the interaction can be in the form of either a push or a pull, as we're seeing right here. So this is a vector quantity, so it's going to have a magnitude or a direction. I can write the force of the push or the force of the pull just right here. It has a magnitude and a direction. 4 common forces that we're going to see in this class. I'll start with the normal force. It's not an ordinary force or anything like that. It actually means perpendicular. And when an object pushes on a surface, the surface is going to push back on the object. If we think about a book on the table or a block on a table, it's going to be pulled down by gravity, but the table is providing a support force in the upwards direction that's perpendicular to the surface of the table. Now, the funny thing is if we look at a surface that is, say, a ramp, the support force is still perpendicular to the table. Another common type of force is going to be frictional force. If I look at an object that has a velocity and it's going across a surface that is not smooth, it's going to be opposed by some frictional force, and it's always going to be in the opposite direction of the velocity. It's going to oppose the motion, and it's also going to be parallel to the surface. Tension force, this is just a simple push or a pull. If I draw a box and I have a handle on there and I pull on the box, there's going to be some tension on that handle or string, shall we say, simply a push or a pull. And last but not least is weight, and that is going to be the pull due to the gravitational attraction of the Earth unlike all the other 4 forces here that I talked about that were contact forces, this is a long-range force. And we're going to talk about gravity and weight in a little bit more detail in a little bit. What are the magnitudes of some common forces? Forces come in all shapes and sizes. If you just look at the dynamic range along this axis right here, you see that we have forces as low as 10 to the minus 47, going all the way up to 10 to the 22nd. That is a huge dynamic range. Weights of things that we're more familiar with might be in this range right here. So between a newton and maybe 10 to the 4th, 10 to the 5th newtons. I said forces are vectors, and that means I can draw a vector arrow to represent them, remembering that vectors have both a magnitude and a direction. If I consider a 10 Newton pull on an object directed 30 degrees above the horizontal, I might draw my horizontal like this, draw my 30 degrees like that, and make sure that I write 10 newtons as the length of the vector. Similarly, a 10 Newton push is going to start away from the object and then go towards it. The reason for that is that it's a push. And I make sure that I write my 45 degrees and my 10 newtons. So you can kind of see a pull, the vector is going to start at the object, and a push, the vector is going to... Because forces are vectors, if I consider 2 forces, force 1 and force 2, acting on an object, I can write the resultant vector of these 2 forces simply as the sum of force 1 and force 2. And we've already talked about adding vectors together. More than likely, you're going to have a force and need to break it down into its components. So suppose I have a force acting on an object and it's acting at some angle. If I consider my x, y coordinate system, then what I'd like to do is I'd like to break that force down into 2 components, force 1, or force in the x direction and force in the y direction. I can also put that guy right over here, kind of think about that parallelogram method, and we can use trigonometry, SOHCAHTOA, to say force of x is equal to the force times the cosine of the angle in between them. Similarly, force in the y direction is going to be the magnitude of the force multiplied by the sine of the angle that is in between them. Please get comfortable doing this because you're going to be doing it quite a bit. Since forces are vectors, we can write the resultant vector as the vector sum of all the forces. So here we have the symbol that means sum, and this is also going to be the net force acting on an object, force 1 plus force 2 plus force 3. Now, we can also break this down into the x and y directions that we've chosen, directions that we're comfortable with, and we can say that the resultant vector is going to be force 1 in the x direction plus force 2 in the x direction plus force 3, 4, 5, and so on and so forth. Similarly, we can say the same thing for the y direction is going to be force 1 in the y direction plus force 2 in the y direction, so on and so forth. So what I'm really doing is I'm writing the resultant in the x direction as being equal to the sum of forces in the x direction and the same for the y direction as well. If we're talking about the third dimension, the z dimension, we could do the same. So force vectors are most easily added doing it componently as opposed to doing it graphically. And if we consider the case where we have force 1, I drew that right here, plus force 2, plus force 3, you can see that force 2 and 3 are already conveniently along the x and y axis. So what we do is we do the SOHCAHTOA break down our force 1, and we write it as force 1 in the y direction plus force 1 in the x direction, and now we can write our resultant vector, our net force, as being force 1 plus force 2 plus force 3 in the x direction, and force 1 plus force 2 in the y direction. The resultant force is probably going to be off in this direction, and we can go ahead and we can calculate the angle and the magnitude of that using the Pythagorean theorem, as well as tangent is equal to the tangent of theta is equal to the opposite over the adjacent. Now that we've talked about forces, now we can start talking about Newton's laws. His first law, simply stated, says an object at rest tends to stay at rest, an object in motion tends to stay in uniform motion, and that seems pretty obvious to us. However, this concept wasn't really introduced until about the 1600s, and it was originally introduced by Galileo, and it has another name, inertia. More properly stated, as stated by Newton, is a body that is acted on by zero net force moves at a constant velocity and zero acceleration. So if we consider an object that is moving with some velocity, then it's not accelerating because it's moving at a constant velocity, and it also has zero net force on it. Now suppose for a minute that I start to introduce something like friction to this problem. And what's going to happen is the friction is going to cause a force that's going to oppose the velocity, and what's going to happen is the velocity vector is going to get smaller and smaller and smaller and eventually stop. Because the velocity vector has changed, it has gotten smaller and smaller and smaller, we would also say that it has accelerated. So forces lead to acceleration. Another way to think about Newton's first law is if you have a hockey puck and you apply a force to it with a stick, then it's pretty obvious it's going to accelerate. Fair enough. Now, if we take my same hockey puck and we have one stick on it applying a force from the left to the right, and then the opponent's stick applying force 2 here from the right directed towards the left, then the sum of forces is going to also be called the net force, is actually going to be equal to 0, and the puck is not going to accelerate. It's going to remain there. One place that Newton's first law is not valid is going to be non-inertial reference frames. A non-inertial reference frame is going to be a reference frame that is accelerating. Now, the book talks about an example for a car that's accelerating. You can read that on your own. I want you to consider, suppose you're on one of those merry-go-rounds, and it's spinning around, and here you are, you're on the merry-go-round, and you're looking at a nearby tree, or I'm going to draw a nearby block. Now you're going to see the block come closer, and then as you're on this side, it's going to appear like the block is moving away from you, and you're going to swing back around it, and the block's going to be moving towards you. And if you didn't realize that you were on a merry-go-round, you would think that this block is moving towards you and moving away from you. It would appear to be accelerating, and it would appear to have some velocity and all that good stuff. But what's really going on is you're in a reference frame that is accelerating. Your velocity is going to be perpendicular to the direction of motion of the merry-go-round. Your velocity vector is changing. So the block appears to move even though it's not. So Newton's first law is not valid in these types of reference frames.